All right, welcome if you're joining us from the future. This is going to be practice quiz 5-1. So practice quiz 5-1, the first quiz under the torque, static equilibrium, and forces practice quizzes. So this is going to be all about this guy walking on a plank that is suspended by this rope. Hello. Okay, one moment. I have to remount my tablet. Boo. Boo. Mapping monitor 2, thank you. Monitor 3, that's what I want. Okay, that should fix it. There we go. Okay, so anytime that I start with something that looks like it's going to involve forces and torques, it's good to, on my separate workspace, draw down the system. So the system that I care about. So here, I'm talking about this uniform beam. The information that I have mostly has to do with the beam and with me. So I have a uniform beam attached to the wall by a hinge, supported by a cable that makes a 30-degree angle with the beam as shown in the picture. The beam weighs 1,000 newtons. I'm standing on the beam. My weight is 500 newtons. So I assume the beam is always in static equilibrium. So the beam comes up multiple times. So that's a hint for me that in terms of the things that I should care about, the beam and maybe me are the two primary components of this system. So I'm just going to draw the beam for now. Okay, there's my beam. So what I'm doing now is I'm setting up a force diagram to describe the situation of me being on the beam and also the beam being attached by a hinge and a rope. So there's like three main forces here that I identify just looking at it. There's the hinge, the point where the where the beam mounts to the wall. There's the rope, the point that applies tension to keep the beam from swinging down around this like pivot point of the wall. And there's me walking along, applying a force downward. Okay, so that's just like the first things that my mind highlights as soon as I see the problem, before I even really read the question. Although if it doesn't jump out at you immediately, then you should definitely keep reading. So let's do that first. So we've got our three parts. I move on the beam further away from the wall. So problem one tells me that I start moving from that position to some new position. Does the tension in the cable increase, decrease, or stay the same compared to when you were next to the wall? Explain my answer. Cool. So that one's going to be more of a verbal type question, although I can support it with text. And before I forget, let me go ahead and lock down. There we go, lock that down. While I'm standing on my new position in the beam, the tension in the cable is 1,200 newtons. How far from the wall are you standing in units of the length L of the beam? This is an interesting one. Okay, so it's telling me now, question 2 asks me, how far is that distance? How far is that in terms of L, the length of the beam? There's L. Okay. In the scenario described in question 2, the force of the hinge on the beam points in this north, south, east, west, northeast, southeast, northwest, or southwest direction. Okay, so I'm given 8 options. Fair enough. Explain your answer. Make sure to include this force in the extended force diagram above. A numerical answer is not needed. All right, fair enough. So because I am maintaining static equilibrium, this final question is one about balancing forces and torques. So I'll just write here to the side that this final question, asking something about a force needed by the hinge, must satisfy the dynamic equilibrium equations, the sum of the torques being 0 and the sum of the forces being 0. Okay, so that's like a brief, just overall, like when I first look at this problem, that's where my attention is directed. That's the links that I make right away. And then based on like what I know, hopefully, or like what I'm most comfortable with, I know which of these to start on. So I'm going to start at the top because I'm the professor and I'm comfortable with everything. Ha ha ha. Okay, so let's start at the top. First, before I start, any questions about the problem setup? Is there anything that's not quite clear about the person walking along, or where these forces are going to come from? The three forces? Okay, doing all right for now? I'm sorry, I can't see if there's a thumbs up. Let me change my view. Do we have to consider the force exerted by the person? Yes, that's right. So there's going to be a gravitational force. Oh, there's going to be 4 forces. You're right. Oh, you got me. There's a 4th force, the force exerted by the person on the beam. So there's the gravitational force on the beam. There's the tension force. There's going to be some kind of hinge force, but I don't know what it is. So I'll just say question mark. And there's going to be the gravitational force exerted by the person. Good stuff. You got me. There's 4 forces. Yep, that's right. So there's going to be 4. 2 associated with some kind of gravitational force, or if you liked them, the person you could consider a normal force, but I'm not going to do that. And finally, a tension force and hinge force. Okay, so let's just draw out real quick a force diagram over here on the right where I have a little bit more breathing room, describing each of these forces and how they're going to need to balance each other out to maintain static equilibrium. So let's make let's do this. This will be, oh no, they made it blue. We'll keep it blue too. All right, we'll keep it blue. So there's the force of gravity, which acts on the center of the rod. The center of the, what is this thing? Hinge? No, it's a rod, right? What is it? Beam. Okay, it's a beam. Fair enough. Okay, so there's a gravitational force there due to the mass of the beam. Vi, I see your question. I'll come right back to it. There's also a tension force F tension associated with the rope pulling up on the beam. And let's see, let's go ahead and mark in that angle. That's 30 degrees. And I realize now I'm using duplicate colors. So this is the pivot point over here on the left, AKA the hinge. And we'll mark the hinge in orange. So there's 2 of my forces. The hinge is going to exert a force. I'm going to leave that one off for now. I'm going to be a little wishy-washy with it. There's also the force of the human. Cool. So there's a force from the human. So we know that the magnitude of that force is going to be m times g. It's just because the human is pressing down on the beam with that much force, with all of their force as a mass. Why don't we consider the normal force on the human in this question? So the system right now, so Vi asks, why don't we consider the normal force on the human in this question? So we don't consider the normal force on the human in this question because the system of interest is just the beam. The beam is the one that's maintaining static equilibrium, here we go, in a way that we care about. So if I were to include the force on the human, I'm talking about a different system. So like there's a normal force on the human, but I'm really concerned about the force on the beam due to the human. That's the one that needs to be countered by this tension force in the rope and stacks with the force of gravity. So to put that another way, if I think about, if I include the human in my system, it may be tempting for me to say, oh, well, the force on the beam is just canceled out by the force on the human. So like it has no effect, right? There's no effect on the tension force. And if you know, that's not true, right? You definitely feel more worried walking out on this thing that the rope's going to break. Yeah. So the human does have an effect on the tension. So you can't just build a bridge that's like has an infinitely long rope and expect it to support you. So that's like intuitively why I wouldn't want to include the human. More generally, I'd say like including the human in our system just doesn't help us address the question of static equilibrium for the rod. So I might also include the force from the hinge on the wall, right? But it doesn't really tell me anything about the rod. It doesn't tell me anything about the maintaining static equilibrium on the rod. Does that kind of answer that? Okay, cool. I think I said Vi a second ago. Sorry about that. V. I know it's V. We've talked about this. Okay. Move on the beam further from the wall. Does the tension in the cable increase, decrease, or stay the same? Okay, so let's talk about each of these forces as I move farther out. So because we're in static equilibrium, the thing that I'm maintaining is that the sum of torques has to equal 0. And similarly, the sum of forces has to equal 0. So the one that I want to focus on for the moment is that the sum of torques has to equal 0. And hopefully it'll be clear why that is in just a second. So let's look at each of these forces and how they contribute to the torque. So there is a hinge force at the pivot point. We don't really get to know what that is. I'm just going to mark it as a little F question mark for the hinge. But the hinge is not going to contribute to the torque. So forces at the hinge aren't going to contribute to the torque. This is by definition of torque. So torque is R times F times sine of theta, where R is the displacement from the hinge, F is the force vector, and sine theta is that angle between force and the displacement vector. So the orange hinge has no distance from the pivot point. So R is 0. So torque due to the hinge is 0. And I'm going really slow on this part, mostly just because oops, all right, that's the wrong place. There we go. Mostly because I want to be sure that I'm expressing exactly like why I'm saying all the things I am. In practice, this should hopefully be a relatively quick one to just talk through. Did I see an unmute? Is there a quick question there? Got Smoothie coming in. Okay, so I'm gonna keep chugging. Once I've gotten to the end of this part, I'll definitely stop and be sure to ask questions, make sure everything's clear and wrapped up. And I'll give a brief overview of it again. If I've lost anybody, please don't check out. We'll come right back. Okay, now the force due to the person, if my person is at a distance delta x, that force is pointing down. So I've got a distance to the person that is separate from the pivot point. So R is not 0. There's also a force, non-zero, and I have an angle of 90 degrees between those two, R and F. So that angle of 90 degrees maximizes sine. So I have a pretty big torque, the biggest possible torque coming from this person, their gravity on this thing right now. So the torque due to the person, I'll just indicate a direction. I apply right-hand rule, stick my palm at the pivot point and curl my fingers. So from your view, stick my palm at the pivot point and curl my fingers. The torque from the person is going to go into the page. Okay. By the exact same logic, the torque due to the mass of the beam itself is going to go into the page. Now, finally, we've got this tension force up here from the rope. So you can kind of see these ones are trying to rotate it clockwise, the two gravity-related forces, and the tension force is trying to rotate it the other direction, counterclockwise. So I can see that that torque is going to go out of the page. Now, one thing to note is that while the others make an angle of 90 degrees relative to the displacement vectors, 90 degrees, this one makes an angle of 30 degrees. So that's going to come into play later. It's just something to kind of hold in your mind. So the tension force is the one where we really have to be careful with that sine function. Okay. All right, so I identified who's responsible for the torques. Now I can finally start thinking a little bit more deeply conceptually about one. So as the person moves farther out, say that they move from their initial position right here. I'm going to copy this. We'll make it a little bit, we'll make this a little schmancy. The wonders of Zyboard. Okay, so say that my person moves from being right next to the pivot point out to a little farther, say right up next to that gravitational force, right up next to the center of mass. So if my person is moved, smiley face. All right, if my person is moved, the force they're exerting is the same. They have the same mass, but the displacement that they are from the pivot point has increased. So R is bigger. The angle hasn't changed. So the torque of the person has gone up. The force due to gravity on the rod itself, on the beam itself, is going to be the same because the center of mass of the rod hasn't moved. Stays the same. I'll just put a little parentheses. And the tension force must increase accordingly. The tension torque has to increase accordingly in magnitude. So they both have to increase in magnitude. I should put magnitude bars on here. Everybody's a magnitude. Okay, so as I move further out, the torque induced by my gravity, the gravity of the person, must be balanced by an increase in the torque of the rod, or sorry, the increase in the torque of the rope, increase in the torque due to tension over here. So because the rope can't increase its distance from the pivot point, and it also can't change its angle, the force must also increase. Okay, so lots of little jumps in there. Repeat. As the person moves out, their moment arm, the R in torque, increases, but the force they exert on the rod stays the same, and the angle between those two vectors stays the same. The gravitational vector, the force of gravitation on the beam itself can't change. So the torque due to the mass of the rod itself is going to be the same. So in order for static equilibrium to be preserved, in order for the rod not to start accelerating downward, or to start pivoting clockwise, I guess is the better way to say that, the tension force has to increase in order to balance out torques. That's the way I'd say that in words. Okay, I'm going to write that, and then I want to give a brief summary and take more questions. So the tension in the cable increases because, let's make this legible, the torque caused by the person on the beam increases, R increases. Since the torque caused by the person must be balanced to maintain static equilibrium, and since no other torque can change, the pivot, or the tension torque, must be the one to increase, must increase to counter the increase in torque of the person. The cable, the rope, there we go, the rope has fixed angle and fixed distance from the pivot point. So F must increase, F tension must increase. Okay, so there it is as a full-on mega answer. So there it is verbally. Ideally, this sort of makes a little bit more intuitive sense than running through all of the sort of like vector drawing and calculation stuff, but I just wanted to be super explicit. I've got a question coming in that says, does the torque on the person not stay constant since F by gravity and mass are constant and R changes? So the torque by, so I'm interested in the torque by the person first. So maybe that's the first thing I should say. It's the torque caused by the person on the rod. So since force by gravity stays the same, with you there, mass is constant, that's true, and R changes. So the thing is, R is changing. That's the thing that causes the torque to change. So for this person, if I draw in their little R vector, here's R, oops, there's my R vector. So as the person moves farther away, the R vector increases. R vector increases in magnitude. The force due to the person stays the same because the person's mass stays the same and theta stays the same. So the torque magnitude increases because R increases while the other two just stay constant. So torque overall must increase as the person moves off. Torque by the person must increase as the person moves over. Torques overall must sum to 0. Was there a question there? Questions? Normally, if it was normally if it was an ambiguous force, would the force required to push down on the rod decrease? I'm not sure I know what you mean by ambiguous force. But so if everything else stayed the same, so if the tension force was a constant, say, and gravitational force due to the rod itself was a constant, then as the person moves out, yes, that necessary force would keep it the same. Or the necessary torque would stay the same. So the force by the person would decrease. So like if R increased and I needed the torque from the person to stay the same, given the same angle, force would have to decrease. Force by the person would have to decrease. But that's kind of removed a little bit from the problem. Thanks for the question. Jordan asks a quick question about the torque RF sine theta. Is the theta supposed to be the angle that has both R and F in the sine? So good. This is, yeah, good. The definition of theta is actually super important. So theta is the angle between R and F. So there's two ways to think about that angle. The first way to think about the angle between R and F, say I've got my pivot point somewhere. I've got my R vector. So here's my PP, P dot P, cool. I've got my R vector. And I've got some force acting at that R. Let's draw it a little bit more zanily. There we go. Here's my force. So the easiest way to think about this angle, if you're drawing out the extended force diagram, is to think about the angle as that angle. So R and F, where the head of R meets the tail of F, that's the angle. This angle between those two. Yeah. So linking the head of R to the tail of F. That's the easiest way to think about theta. There's an alternative way to think about it if you don't like that way, which is if I drew both of these objects at the origin, if I drew both the R vector and the F vector at the origin, theta is the smallest angle between them. And even though these angles are different, they're the same when you apply sine to them, when you apply the sine function to them. So this is, I think this one is this one plus 90. I think that makes sense. Yeah, so I think if we call this one theta 1, this one theta 2, theta 1 plus 90 degrees equals theta 2. And when I apply sine to either side, they're the same. And that's just like a symmetry of sine. So either of these will work. I think most people prefer the one that I've just circled, but if you really don't like it, if you're a little bit more like, no, vectors have to start from the origin, then this is also true. Okay, good questions all. So again, how did I address this problem? What I did was I looked at each of the torques. First, I had to identify where all the forces came from. I looked at the torques caused by each, and then I looked at how the torques would change under the conditions specified by the problem. So the person moving over means that their torque is going to increase. The torque that they put down on the rod is going to increase. The gravitational torque can't change. The hinge can't contribute to the torque. So in order to maintain static equilibrium, this torque, the torque by the rope has to increase. That's going to increase that tension force. Okay, and again, I'm kind of like, that was that little set of logical jumps I went through was much longer form if I were to actually do it out. So I would recommend on an actual test, maybe doing up to here written out. I mean, and you can write out as much as you want, of course, but ideally the rest of this becomes intuition. Like, okay, the gravitational torque can't change because R and F can't change. The person's torque does change because he's moving out, and the tension force must change accordingly to maintain static equilibrium. And then write it, done so. Okay, but that's more of like a test taking strategy type thing. Okay. 2. While staying in my new position on the beam, the tension of the cable is 1200 newtons. How far away from the wall are you standing in units of the length L of the beam? So this is actually, it looks bad, but it's really not that bad. This is going to be one that's not terrible. So I want to know how far away from the wall am I standing in units of the length L of the beam. Cool. So let's do it. This is just going to be that addition of torques. So there's only 3 meaningful torques because the hinge can't contribute. So I have to consider the person's mass, the gravity of the rod, and the tension force. So let's do that. We'll balance them out. So I'm going to sum the torques. They have to sum to 0. We're applying that condition of static equilibrium. Now I'm choosing to do this because it's the only way for me to get at a relationship between the tension in the cable, that's a torque of the cable, and the what do I call this? My distance, like the distance of my standing. These two are linked in that the sum of the torques must be 0. The torques include a distance, so that's a hint that if I want to find this distance, torque's a good place to start. And also, I'm trying to unite these 2 forces. So I'm trying to unite my gravitational force downward and also talk about a tension in the cable, a force in the cable. So that's kind of how I leapfrog over to thinking, okay, this is really about summing those torques. All right. Questions about the setup? Why I've chosen this? I think that's the hardest part, right? Is like picking the thing to start with. So questions welcomed. Or questions about the first part too. If you're still like, wait, why is that from the first part? Happy to talk more about that.
Okay, yeah. So for the first part, you said that the gravity of the beam was facing downwards because the pivot point was to the left. If the pivot point was to the right, would the gravity have the direction be pointing at us?
That's right. So so let's say the pivot point was this green point over here now, and I get rid of this old pivot point. Then in that case, applying my right hand rule, again, sticking my hand at that pivot point, now on the right of the rod, and gravity curling down still for that rod, the torque now points toward me, so out of the page. Yep, that's right.
Okay, thank you.
Yeah, sure thing. Good check. Okay, let me go ahead and, all right, back to the default. Okay, so I'm in my new position. The tension of the cable is 1200 newtons, and I want to know how far from the wall I am in terms of the unit's length L of the beam. So this is going to be a torque sum type problem. What I'll do is I'll go ahead and say that the tension force is a positive torque. It's going to generate a positive torque, rotating me in the counterclockwise direction. And I'll say that the other 2 are going to be negative. They're going to go in the opposite direction. That's kind of just a sign choice. Not a huge deal either way. But so what I'm going to say is that torques, I'll say that torques out of the page are positive and torques into the page are negative. So let's talk about our torques. There's a torque due to the tension. Let's draw that one first because it's the most annoying. So the sum of torques, just trying to make my sum a vector. That's funny. Okay, the sum of torques, we'll start with the tension. So tension torque plus, or I'll say minus the torque due to, or I'll add it, but we'll know that it ends up being negative. The torque due to the person plus the torque due to the gravity of the rod itself, the force of gravity on the beam itself. Those things have to sum to 0. Those are my only 3 sources of torque. So let's calculate them. The tension torque is going to be, it's going to be the force of tension times L, that's force times distance, times the sine of 30 degrees. Is that comfy? So to be super explicit about that, and I'll erase this vector in a second, but my R vector for the tension force goes all the way out there, and it has a length of L. It's one length. So that's why I put the L here. the angle between the r vector and the tension force is 30 degrees, as given in the problem. So that's why I've made 30 degrees here. Okay. Now for the person. So the person's how do I say this? The person's torque is rotating is trying to rotate clockwise. So I'm going to put a minus sign out front. It's going the opposite direction of the tension torque. So this person's tension, how do I say this? This person's torque. Yeah, their torque is going to be given by whatever their distance is times their gravitational force. So my weight is 500 newtons. So I'll say my weight person. So I'll just say force of gravity on person is fine. Force of gravity on the person times whatever my distance is. I'm going to call this just delta x. That's the thing I'm ultimately interested in solving for. Delta x, my distance, times sine of 90 degrees. So I'm just going to say theta is 90 degrees. I'm going to drop the sign. So sine of 90 degrees is just 1. Torque is as big as possible for this person. Okay, and then minus the force of gravity on the bar itself. So force of gravity on the beam times the distance to the center of the beam from the pivot point. So that's just going to be L over 2. L over 2. And again, the angle formed is 90 degrees. So sine of 90 degrees is 1. So I'm going to drop the sign. So a couple of jumps there. One jump that I made is saying that, okay, because the gravitational torques, or the gravitational forces rather, make an angle of 90 degrees with the displacement vectors, sine of 90 degrees is 1. So there's a little 1 here modifying each of these for the sine part of the torque. The other thing I had to think about a little bit was, okay, what are these distances in terms of L? So the tension force is acting all the way out at L, the length of the rod relative to the pivot point. The gravitational force on the rod is acting at a distance L over 2 because the center of mass of the rod is, halfway between the left side and the right side. Yeah. Questions at this step? We still following? We zoned out? Give me a thumbs up if you're like, yeah, I'm all right. Thumbs down if you're like, I'm not all right. And give me, I don't know, a clap if you're like, I'm trying to go to sleep. Get me out of here.
Question?
Yeah, question.
So whenever we have like a problem involving gravity, do we always assume it's affecting only the center?
Good. Yes. So gravity can be treated as though it's affecting only the center of mass. That's right. So I'm trying to give an example. I got a Wii. Hello. If I have an object and I am holding it up, right? I can take my whole hand and distribute out a bunch of different forces to hold it up, or I can just find the center of mass. Hello. You'd think it'd be in the center, right? Right. I can find the center of mass and just apply a single force there. So yes, we can treat gravity as working only at the center of mass, working only at the center of mass of the object, without losing anything. Is that okay, Jordan?
Yeah, thank you.
Okay, good stuff. Yeah, sure thing. So it's not necessarily the center of the object, but it's the center of mass. So like if I had something that was heavier on one end and lighter on the other, then the center of mass would be shifted more toward the heavy end. But we don't typically ask you to, we don't ask you to do center of mass calculations in here. That's a bit much. So it should be obvious where the center of mass is. Like here for the rod, it's right in the middle. Okay. So there's our formula. Boom. I've got my torques. I've got the appropriate signs on each of them to indicate whether they're going into the page or out of the page. I've got everything in terms of L. Now all I have to do is plug in some numbers and solve. So the force of tension I know is 1200 newtons. I'm going to drop units because I'm feeling kind of lazy, but it's just 1200 newtons times L. Sine of 30. Never learned the unit circle. It's just a half. So 0.5. That's going to be embarrassing someday. Right now, it's still funny. All right, minus force of gravity on the person is 500 newtons. That's from up here. Times delta x, that's the thing I'm solving for, so I'll leave it as a variable. Minus force of gravity on the beam. So the beam weighs 1,000 newtons, so that's 1,000, times L over 2. One thing that I'd like to call your attention to is that in this problem, they've already given us the force of gravity. They don't even make us go through the hoop of like using the mass and multiplying by 10. So one way that I like kind of can double check myself to be sure that I really am looking at a force here is just with the units, right? So if that's units of newtons, then I know it's a force already. I don't have to worry about it. Okay, now let's solve. So I'm trying to figure out if I can skip any steps. Yeah, let's just do it out. We'll do it out completely. That's fine. So this is 600L minus 500 delta x minus 500L. Okay, so we subtract those. We're left with 100L. So I'm going to, there we go. So that equals 100L minus 500 delta x. So what do I get out? I get minus 500x. There we go. So I get out that delta x equals L over 5, or 0.2L. Okay, one intuition check I had for this problem lined up is that my delta x should not be greater than L, right? So if I had like 1.2L, well, what would that mean? That would mean that my person is like has walked the plank. They're already way out here and getting ready to fall into the ocean or whatever. So the fact that it's only 0.2L indicates to me that they are right around here. Cool, around a fifth of the way down the beam. So this feels comfortable to me. I haven't checked this against the problem solution, but just looking at it, it looks okay. We got another question coming in real quick. So is the angle for the force of gravity always going to be sine 90? In general, no, it doesn't have to be. So a counterexample, when the angle from the force of gravity is not 90, is if my beam were rotated. So my beam's rotated and it's still got that gravitational force on it, right? Here's my pivot point. EP, here's the force due to gravity. And my R vector would then point like that to that force. So here the angle is greater than 90 degrees. Naomi, hopefully that answers. Is that okay? Thanks for the question. I think that is a common misconception, so it's good to clear out. So we do always want to double check R and the force of gravity. What is their angle? The only time that the force of gravity should be at an angle of 90 degrees with R is when R is like, I guess, maybe like you could say parallel to level, parallel to the ground. Assuming flat ground. Yeah, sure thing. Okay, so here we are. Question 2, again, as a summary, what did I do? First, I took a look. I was like, all right, I know a force. I want it in the tension of the cable. That's weird. And I know that I'm standing some distance from the side, but like, what do I do from there? How do I link those two things? Well, I know that we are in static equilibrium. Static equilibrium. So the two conditions of static equilibrium are that the sum of forces must be 0 and the sum of torques must be 0. The sum of forces being 0 means that I have to know not only all of these 3 forces, but also the hinge force. So that feels like too many variables, like too many things that I don't know. The sum of torques being 0, maybe this is more workable. Maybe I have enough variables to do that. And it turns out that I do, as I kind of explore down that avenue and work out the problem. So I add the torques together, being careful of my signs, making sure that the torques that point, say, up go the opposite direction, have the opposite sign of torques that point down, or I guess I should say into the page. out of the page and into the page. Sorry, kind of changing my reference frame now. So here I've made the one that is out of the page be positive, and I've made the ones that are into the page be negative. Oops, misdrew an arrow. This one actually goes here. Sorry about that. So being careful with my signs, and then I just solve it out. Solve it out as in do the algebra. And I get out, boom, 0.2L. All right, last part. Unless there are more questions, please. Questions on 2. Okay, that was one Jeopardy theme song. So I'm gonna assume we're okay to keep going. Please, as you know, as questions come up, please do ask them. Or if you're not feeling like asking a question right now, want to talk about it later, feel free to send a message, good shot, that I can make a whole class announcement or something like this about these problems if they're throwing us for a loop. Okay. There we go. Aha, one Jeopardy theme song later. For number 2, how do I know whether to make the in-out direction positive or negative? So within a problem, you just set one and go with it. So I chose to make out of the page positive because I don't know how to say this super well. There was a larger mathematical convention that out of the page usually means positive. In terms of like for us, the class, it doesn't really matter. You can pick either and you'll get out the same answer. So you can pick, I could have picked just as easily for into the page to be positive and out of the page to be negative. The math would have worked out the same. Yeah, I just would have had like negative signs on either side, which would then cancel at the end. So yeah, practically, it doesn't really make a difference for us. I'll tell you that the reason why I choose to do this is because if I've got a torque out of the page, that tells me that the object is trying to pivot in the counterclockwise direction. And if I measure my angle relative, if I measure an angle relative to the x-axis, if I measure the angle this way, that corresponds to a positive angle, whereas this direction corresponds to a negative angle. So like in terms of my decision to make out of the page be positive, that's why. I think it's a little bit more notationally clean, but again, like we're not testing you on that kind of like vocab. So it's up to you picking which one's positive, which one's negative. But just as a piece of trivia. Okay, last problem. 3. In the scenario described in question 2, the force by the hinge on the beam points in north, south, east, west, yada, 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 or southwest direction. Explain your answer. Make sure to include this force in the extended force diagram above. So, not actually that bad. Let's give it a look. This is a question about the second part of the static equilibrium constraint. So, we've already seen that the torques have to sum to 0. That means that the torques caused by the person, the gravity of the rod itself, and the tension force have to cancel each other. What's going on out there? All right, but that doesn't by itself tell me that the forces are going to be 0. In fact, if I just add up the 3 forces that I see right now, just kind of doing a visual addition of these 3 forces. There's the gravity of the person. Here's the gravity of the rod. Here's the force of tension. So I can already see that, these don't really, these don't add up to 0, right? So I'm going to need to balance this somehow with a force that acts at least with some component to the left. So let's scale these appropriately. I feel like right now I have not scaled them appropriately. Let's make them the right size. So the tension force, just using the scenario described in 2, I know the lengths of each of these force vectors. Like I have numbers for each of them. So the tension is 1200. This one's 1200 in length. Gravity on the beam is 1000. And the size of my weight is 500. 500 newtons. These are all newtons. Okay, so again, kind of doing like a head to tail type vector addition. The force due to gravity has length like 10 units, I'll say, 1,000 newtons. The force due to the person is half that big. Boom. And then the force of tension has like, I'll say, quote, 12 units. Like it's slightly longer than the blue one, but it's angled at, oops, it's angled at 30 degrees. Here we go. So something like that. Boom. Okay, so that is the force of gravity on the beam, the force of gravity on the person, and the force of tension. All right, so these things clearly don't sum to zero, right? If they sum to zero, then all of my, like the sum of my vectors, the head to tail sum of them, would point me right back to the origin. So I need a hinge force to take me back to zero. There's my hinge force. So the hinge force is going to point in the northeast direction. Hinge force is going to point in the northeast direction. So I'll go back to that picture for a minute, see if there's questions here. So again, the constraint I'm working with is that the sum of forces must be zero. That's required for static equilibrium. If the sum of forces was not zero, then the whole system would start accelerating in one direction or another. So the sum of forces being zero means that there's no acceleration. Yeah, and I need that if I have static equilibrium, because otherwise it wouldn't be an equilibrium. It would just start moving. Yeah. Okay, questions. How did I set this one up? What is this vector addition? What are you doing here? Things like that.
So you said that for tip to tail addition of the tension and the force of gravity, there's a 30-degree angle there.
Yes, so there's a 30-degree angle. I should be specific. There's a 30-degree angle here. There's a 60-degree angle here. So there's a 30-degree angle that the tension force makes with the horizontal. Does that help, Jordan, or is that still kind of iffy?
It helps, thank you.
Okay, good stuff. Yeah, sure thing. Thanks for the question. Okay, so by way of a true answer to number 3, force points in the northeast direction. And the reason for this is that, 1, the forces must sum to zero to keep the system in static equilibrium. And 2, the other 3 forces, gravity on the beam, gravity on the person, and tension, sum to a vector pointing southwest to bring us home to the origin. We need, that's grammatically incorrect, or whatever. We need a northeastern force. The hinge saves us. Yay! All right. The hinge hero. Sweet. Okay, so that's about all I had prepared. I think now would be a good time to open up to both general questions and any lingering questions about this mini quiz. What I'll do is, if there are any general questions about the quiz, I'll keep the recording going. If we want to break it out into like individual things, like or quiz topics, I'll probably stop the recording. So just let me know if there's any more remaining questions about the quiz, or sorry, about this practice quiz. Thanks, Jasmine. Okay, so let me go ahead and stop the recording.
One last question real quick.
Yeah, go for it.
So when we're using like the R perpendicular or F perpendicular, we get sine entirely?
So the R perpendicular or the F perpendicular kind of have the sine built in. So R perpendicular is R times sine of theta. That's already what it is. So, or F perpendicular is F sine of theta. So if I were to rewrite my tension magnitude as F perpendicular times R, that's equivalent to F sine theta times R, which is of course just the same as RF sine theta.
But since it's 90, we just kind of don't write it.
That's right. So the reason I chose not to write the sine theta, I mean, you can still write it. There's no problem with writing it. But I just kind of dropped it because I have limited space here. That was a little clunky sometimes. Yeah, so like over here when I didn't write it because I already knew that the angle was 90 degrees. And so sine of 90 is just going to be 1. Yeah, so if you like, do a 1 there and a 1 there. Does that make sense, Jordan?
Thank you.
Yeah, sure thing. More quiz questions or practice quiz questions? Okay, I'm going to go ahead and end the recording. Thanks for joining us from the future, everybody. Catch you next time.